I will check. I will be checking that. But anyways, would you turn on the lights? I don't use that one yet. So basically, yesterday we were talking about the signals, digital signals, and what we did was basically couple of things like the how do you do sampling on Octave in so basically how to make the sampling points or sampling indexes, and that basically you just set a value, for example, from -1 to +4 in this case, and that would be setting up this basically region of interest for your data. Then if you want to create, for example, the unit impulse function, then that would be just simply well, dd equals casting to double of checking that when n equals to 0, like that, and unit step likewise. Sampling a function, any function would be if you have function envelope looking like that, x of t, then you would just evaluate the function on those points, and that's it. So x of n equals x at value of n time the sampling time ts, where you need to know the ts, which is also the 1 over the sampling rate. Okay. So practically almost everything yesterday is put into this one small picture, except one more thing, the TS here. It's simply the time difference between two samples. Okay, that's almost all. And it took what, 4, 6, 5 hours? Oh boy, I'm you know, slow explaining things. So yeah, so that's what we covered yesterday, and then we had basically these exercises, playing with the unit impulse, playing with this creating indexes, playing with all kind of other stuff. And one more application area. I like the audio applications just because it's something tangible. You can actually test what happens, and for example, when we go to filtering, it's basically very good to idea to have audio samples. Then you can hear what is the difference. Okay, for that reason we also can, if we put the time scale here, t, that would be 0. That's ts, 2 times ts, 3 times ts, and so on. So how to generate a sound sample? You can set up the a vector of sample points by the same colon operator, except now you use 2 colons, and for example like that will be 1 second long sound sample with this sample time, meaning that sample rate. Okay. And then one last thing yesterday was about how to generate the some noise, so some uncertainty to the data. So basically for each of these data points we can add some noise. And noise was just random numbers of size of your data. Oops. For example, like that. Good. I will also add here one small thing what you need to, it's usually has taken a while to figure out the signal to noise ratio. The definition of signal to noise ratio is 10 times log of 10 power of signal divided by power of noise. And basically, this is exactly the same as that one, and the variance of signal divided by not power, but, variance of noise. And these are just statistical measures of the power. Okay, good. So basically, on that one exercise today, or the first exercise, the signal to noise ratio is given. You can measure the variance of the noise. This is basically just the variance signal. Variance of the signal what you are analyzing here or generating. Then basically, based from this formula, you can calculate the variance of the noise. Okay, that's what you calculate. And when you're adding let's mark it for S and N O. When you are adding this signal and have the noise added to the signal, you basically must multiply this one by the deviation of the noise you calculated. Not squared, but like that. So basically, this is just the variance, square root of variance. Right. Where does that one comes from? Well, magic. Or actually, you can take that one out here. Then you will be calculating the standard deviation. But then that will be 20. Okay. So like in the AC circuit theory, the signal to noise ratio could be calculated as 20 times log of 10 of signal amplitude divided by noise amplitude. Okay, but the same way here. So when you are doing the this was it exercise 9, where you have the given signal to noise ratio. Basically, you need to calculate the noise variance and use that one to scale the random numbers to have the required signal to noise ratio for your sample. Okay, good. So now you can start working. I think I'll be just hanging around here and make sure that you can progress on your exercises, and yeah, I think it'll take until lunch break, so you have plenty of time here. And after lunch break, well, we will have about 4 hours session where I cover the second topic and the second lab. Okay, start working. And I would like you to actually start also communicating, work together. No silence, please.